Now let's look at shear joints. In order to calculate the load taken by fasteners under shear loading, the center of relative motion between the joint members, the centroid, must be found first. So what happens is, in this diagram, I1, I2 till I5 represent location of individual bolts. So we will have a bolt pattern that will be given to us. So whichever bolt pattern is given, the first thing that we need to do is we need to find the centroid. Once we have obtained the centroid, then with respect to the centroid, we can calculate our moment, we can calculate the forces such as your primary shear and secondary shear acting on these individual bolts, and finally we can calculate the resultant load. So what happens is, this is a very good example. So you've got two columns, and then the columns are joined using a beam, and then what we have is the beam and the column are joined together using bolts, and then we have a force acting. So the first thing that we do is, let's say we're looking at this side. So we've got 4 bolts, so we'll have A, B, C, D, and on these bolts we'll have forces acting, and these forces acting on the bolt are due to two things. One is the direct shear, which becomes your primary shear, and the other one is due to the moment that is acting. So there is a moment about the centroid O, and this moment gives rise to a secondary shear, and the secondary shear will be calculated using appropriate formulas. So looking at the previous scenario of the load scenario, what happens is the load taken is in two ways. One is the direct shear, the primary shear, and the other one is the moment loading, which is your secondary shear. And we calculate our primary shear by using expression 8, and your primary shear F single prime is simply V over N. V is basically the load acting on that beam, and N is the number of bolts. So if you have 16 kilonewton acting on that particular beam and you've got 4 bolts, so your primary shear will become 16 divided by 4, which is 4 kilonewton. Right. Then the secondary shear is found using equation 9. So which says that F double prime N is equals to M 1 Rn divided by Ra squared plus Rb squared plus Rc squared plus Rd squared. So at the moment the formula does not make sense, but later on as we solve an example it will be much clearer. So here N indicates the bolt that you are looking at. For example, whether it's bolt A, bolt B, bolt C. So naturally if N is A, then Rn will be Ra as well. So it is the distance of bolt A from the centroid. So that becomes Ra. And in the denominator you've got Ra squared, Rb squared, Rc squared, Rd squared. So if you've got 4 bolts, then Ra is the distance of bolt A from the centroid, so that becomes the radius. Rb is the distance of bolt B from the centroid, so that becomes Rb. So if you've got 6 bolts, then you will have 6 different radii that needs to be accounted for in the denominator. So we'll use equation 9 to calculate our secondary shear. Then what we do is, once we have found our primary secondary shear, so the resultant force acting on that particular bolt is simply obtained by doing the vector sum, which is given by equation 10. So it seems a little bit easy, but it will become more clearer as to how we do these calculations when we look at an example. So now let's look at example 4. So what we have is, we have a figure and it shows a 15 by 200 mm rectangular plate steel bar cantilevered to a 250 mm steel channel using 4 tightly fitted bolts located at A, B, C and D. And then the load, the applied load is 16 kilonewton. So what happens is, the dimension of the flat plate is given, which is mounted onto the C channel column. And then what we have is, the width of this particular plate is 15 mm. The width of the C channel is given is 10 mm. So what happens is, we've got our bolts A, B, C, D. So this is our bolt pattern, and we see that the dimensions or the distance between A and B, C and D, D and E are given. So from I to O is 75 mm, from O to D when we see here is 75, and then we've got 60, 60. Now the first thing that we need to do is, for this particular bolt pattern, we have to find the centroid. Since it's a regular pattern, it's a rectangular pattern, so basically your centroid is right over here. So what happens is, the distance of the centroid from the point of application of this applied force is simply 300 plus 50 plus 75. So that's something that we need to consider. So the distance of the centroid to the point of application of the force of 16 kilonewton, so that distance is 300, which is over here, plus 50 and then plus 75. So that distance is important when we do our calculation a little bit later. Now what happens is, we have to find this resultant load acting on each point. So point O is the centroid of the bolt pattern, and it is found by symmetry because it's a regular pattern, a rectangular pattern, and we know that the centroid of any rectangle is basically the center of that rectangle itself. So we know, okay, this is the centroid O, and we know the distance of that centroid from the point of application of the force is 425 mm. So again, this is your centroid. So the distance of the centroid to the point of application of that force is basically 300 plus 50 plus 75, which is 425 mm. So the first thing is, we know that the shear that is acting, or the applied load that is acting on that particular beam is 16 kilonewton. So okay, force is 16 kilonewton. The moment, again this moment is about point O, about the centroid. So the moment about your centroid is simply 16 kilonewton times the distance dc, which is the distance of the centroid from the point of application of this force F, so which was given as 0.425 meters. So we know that our moment about our centroid is 6800 Newton meter. Now what happens is, looking at this bolt pattern, we can see that this is I, B, C and D. So this is Ri, distance of bolt I from the centroid. This is RB, the distance of bolt B from the centroid. When we look at the geometry that is given to us, we can say that this distance of bolt I from O, the centroid, is same for all. So RB, RC and RD are same for all. And what happens is, looking at the geometry, we can calculate our distance OI, which is basically your RI, as simply, this is a right angle triangle. So you've got 75 over here, we've got 60 over here. So 60 squared plus 75 squared, whole thing square root, we get our radius, or the distance of bolt I from the centroid is 96 mm. And the geometry is such that RB, RC and RD are going to be exactly the same. So the first thing is, we can calculate our primary shear, which is nothing but V divided by N. So the direct load that was given was 16 kilonewton. So 16 kilonewton divided by N. N is the number of bolts. So we just got 4 bolts, I, B, C, E, D. So 16 divided by 4, we get 4 kilonewton. Now for the secondary shear, we use this expression, F double prime N is equals to F M1 Rn divided by Ra squared plus Rb squared plus Rc squared plus Rd squared. Now what I'll do is, I will calculate the secondary shear acting at bolt I. So this becomes Ri, the distance of bolt I from the centroid. So your moment was 6800 over here. The distance Ri was 96 mm. So converting that to meters is 0.096. Then what we have is, we have Ra squared plus Rb squared plus Rc squared plus Rd squared. Looking at the geometry, the distance of all the bolts from the centroid are equal. So that's why all these values are same. So once we do this calculation, we get our secondary shear as 17.71 kilonewton. And what happens is, since all these bolts are located from the centroid at the same distance, so what happens is, the secondary shear acting on all the bolts is same, which is 17.71 kilonewton. Now what happens is, the primary and secondary shear forces are represented on each bolt. So you are given this diagram was given as part of your problem. So what I have done is I have simply said, okay, I, B, C, D. This is not drawn to scale. I'm just drawing this and I'm representing all the forces acting on the bolt. So what happens is primary shear acts in the same direction as the applied load. So your applied load was acting downwards, so your primary shear will act in the same direction. So you'll see that on bolt I have indicated my primary shear, which is F single prime I, which is acting downwards. Now at bolt B, again your primary shear at B, which is F single prime B, acts downwards. Again F prime C acting downwards, that's your primary shear. At D, F prime D acting downwards, that's your primary shear. Now what happens is, how do I represent my secondary shear? What do I do? And as to how do I indicate that in which direction is my secondary shear acting? So you've got your bolt pattern A, B, C and D, and you will connect each bolt to the centroid. Done. Now what happens is your secondary shear, in order to represent your secondary shear, it's very simple. What we'll do is, the first thing, when you look at your centroid O, the moment caused by this force F acts in the clockwise direction about your centroid O. So same thing here. So your moment about centroid O is acting in the clockwise direction. So what would happen is, we represent our secondary shear based on the global moment. So global moment about point O was in the clockwise direction. So now what happens is, when you look at this lever arm, the moment has to be clockwise. So the only way this moment on this lever arm can be clockwise is if my secondary shear is acting in this direction. So when you look at this force acting about this centroid O, you'll see that it's going to cause a clockwise moment. Now when I come to this lever arm, I need to represent my secondary shear in this direction. So this force is going to cause a moment clockwise. When I come to this side, my secondary shear is in this direction, right? In this direction. So again this F double D will cause a moment clockwise about point O. Over here again this secondary shear will cause a moment in the clockwise direction about point O. The thing that you need to remember is that this secondary shear is 90 degrees to this lever arm. 90 degrees to this lever arm. So draw your free body diagram and draw it in such a way that this seems to be at 90 degrees. Later on when we do our calculation, we won't be using our graphical method, but we'll be using our analytical method to calculate the results. And so once we have represented the primary and secondary shear on each and individual bolt, we can calculate our individual forces. So once more, the secondary shear has to be in the same direction, or it should cause the moment about point O in the same direction as the global moment. So global moment caused the moment clockwise around point O. So all of the secondary shear acting on this lever arm, let's say O to I, will cause a moment in the clockwise direction. The next thing is, the resultant is found using cosine rule, and what it says is that cosine rule, what happens is side C and then the angle representing side C. So C squared is equals to A squared plus B squared minus 2AB cos theta C. So this is the cosine rule that we'll be using. So now what happens is, I'll just look at bolt I. So the forces acting at bolt I are given. So what I can do is, the first thing is I have to calculate this angle alpha. That angle alpha was given by alpha is equals to tan inverse of 60 over 75, because in your diagram you knew that the distance of I, this distance was 75, this was 60. So you can find your alpha. So alpha was 38.7 degrees. So what I do is, whenever you draw your free body diagram, whenever you're representing your forces, add these vectors head to tail. So this is my resultant, and I know that this is the angle that I'm going to look at. So that is my angle that I'm going to calculate. So if this is 38.7, so this is 90 degrees. So this is 38 90 minus 38.7, so it is 51.3. So this becomes again 90, this becomes 38.7. And then what happens is eventually you'll find